in the last section, we introduced the idea of similar matrices. So if we have two matrices A and B, we say they are similar if there exists some invertible matrix P, so that B is equal to P inverse times A times P. And the sort of justification we gave for exploring this concept was that a matrix, if two matrices are similar, they share a lot of properties. There's a lot of properties that they have in common. And sometimes maybe matrix A is kind of hard to work with. Maybe it's inconvenient to work with. So sometimes it's easier to work with some other matrix B, some matrix that's similar to it. In this section, we're going to explore what might be that easier matrix that we want to work with. What might be a nice similar matrix that we could turn to that would be easier to work with, but have a lot of those nice properties that the original matrix A might have. And as we kind of maybe think about the matrices that we've worked with that are easy, one of the easiest kinds of matrices is a diagonal matrix. So we're going to explore to what extent a matrix can be similar to a diagonal matrix. Okay, so just as a reminder, recall D is diagonal, or is a diagonal matrix. If the only non-zero elements of D occur along its main diagonal. Anywhere except its main diagonal, the elements are only zero. And we like diagonal matrices. It is super easy to take the determinant of a diagonal matrix. It's easy to identify the eigenvalues of a diagonal matrix. It's easy, if the diagonal matrix is a coefficient matrix, it's easy to solve a system of linear equations if we have a diagonal matrix. We can quickly find the rank of a diagonal matrix. Diagonal matrices are really, really nice to work with. Okay, so if we can take some arbitrary matrix A and then show it is similar to some diagonal matrix D, if we could work with matrix D instead, boy, that'd be a lot easier than working with some other matrix A directly. Okay, so let's explore this idea. Is this even possible? So in order to do this, so let's explore if we can set, or if an n by n matrix A is similar to a diagonal matrix D. So to do this, I know D is a diagonal matrix. So I'm going to set the diagonal entries of D equal to lambda 1, lambda 2, all the way down to lambda n. It needs to be an n by n matrix, since A is an n by n matrix, right? It needs to be a square matrix of the same dimension. Notice I didn't put any entries up here or down here. It's common if we leave those blank for it to mean that those are zero. It just saves us a little bit of writing, makes it a little bit more obvious what's going on. If you want to, you could always put the zeros there. It doesn't hurt anything. Okay, but I'm going to leave them out. That emphasizes that, hey, we have got a diagonal matrix here. There are zeros above and below that main diagonal, right? I'm also going to define the columns of matrix P. P being the invertible matrix that we multiply A by to get our matrix D, our diagonal matrix D, hopefully, right? We want to know, we don't even know if this is possible at this point. We are just exploring this idea. It would be super nice if we can make a matrix A similar to a diagonal matrix D. So the columns of matrix P, let's call them x1, x2, all the way to xn. Okay, and we want P inverse AP to be equal to D. So what I'm going to do is I'm going to left multiply both sides of the equation by matrix P. That will clear out P inverse on the left-hand side of the equation. And I get a left multiple of matrix P on the right side of the equation. Okay, and I want to kind of explore this. So let's plug in what we know. I know matrix P is equal to this matrix with columns equal to x1 to xn. And I know matrix D is a diagonal matrix, and I've called those diagonal elements lambda 1 to lambda n. So let's plug those in. And I, of course, know what the result is we're looking for, so I know just the right way to explore this idea so that we get what we want. You could imagine mathematicians, when they first thought up this idea, that it may have taken them a little bit more work and more time to get exactly what they want. So I have A times P equals, and now I'm going to have matrix P on the other side of the equation. With columns equal to vectors x1 to xn. And then I have matrix D with just its diagonal entries lambda 1 to lambda n. Okay. All right, now I kind of want to think about each column of the product on each side of this equation. All right, let's think about the right side first. I think it'll be a little bit easier to think about. So for each column, if I want the first column of this matrix, I'm going to focus on the column here. Because remember, when we multiply two matrices, it's row times column, right? And so if I want all the entries in column 1 here, I want to take column 1 here and multiply it by each row in matrix P. Okay? But notice that the only non-zero entry, or potentially non-zero entry, in my diagonal matrix is the first one, right? So no matter which row this first column multiplies by, the only element that will potentially not be 0 would be lambda 1 times the element in x, the first element in x1, right? And then in the second row, it'd be lambda 1 times the second element in column x1. And the third row would be lambda 1 times whatever the third element in column x1 is. So it's always going to be lambda 1 times the corresponding element in column x1. And so if I look at the whole column, I'm going to just get lambda 1 times x1. Okay? And I can actually do that for every column. If I want column 2 of my product matrix, that means I want all the products involving the second column in the second matrix. Now, the only non-zero entry is lambda 2, and that's in row 2, column 2. And so if I take the dot product of this column with each row in the first matrix, the only column that will matter here are the entries in column x2. because everything else will be multiplied by the zeros in this column. Okay, so I get lambda 2 x2. And so on until I get lambda n xn. So hopefully that makes sense. We are kind of viewing the matrix multiplication on a more macroscopic level, so it might be a little hard to keep track of, but if you're uncertain, give it a try. Take a example matrix and multiply by a diagonal matrix, maybe something like 1, 2, 3, 4, 5, 6, 7, 8, 9. And you could try multiplying it by the diagonal matrix with elements 1, 2, 3. And you will see that the product would be, in the first column of the product, you get this times this column. Okay? And the second column of the product matrix, you get this times this column. And the third column of the product matrix, you get this times this column. Okay? If you want to try it out, just to confirm that the result is true, give it a try. It will help you understand what's going on a little bit better. All right, let's go to the left side. Left side's even, if anything, a little bit trickier. But the idea is largely the same. Okay? I want to go column by column. And remember, for each column in the product matrix, for each entry in a matrix product, I multiply the row of the first matrix that corresponds to the row I want to be in with the column of the second matrix where the column is where I want to be in. So if I'm focused on the first column, then I'm looking at all the products involving the first column of the second matrix. Okay? So all the products involving the first column of the second matrix, well, that's just going to be all the ways that I can multiply matrix A by that first column. I'm going to get A times column x1. That's going to be the first column of my product matrix. And same thing for the second one. If I want the second column, it's going to be matrix A times the second column of the second matrix. AX2, and so on. Okay? All right, now we're almost done, because this tells us something really interesting, because now, because these two matrices are equal, each column in the two matrices, the corresponding columns in the two matrices are equal. So the first column in the matrix on the left must equal to the first column on the matrix on the right. The second column in the matrix on the left must equal to the second column of the matrix on the right, and so on. Oh, and this tells us something really important, because what do we see? This should look familiar. We say A times vector x1 is just the same as scalar multiplying x1 by lambda 1. Matrix A times vector x2, if we multiply those together, it's just the same as scalar multiplying the vector x2 by lambda. Lambda 2, I should say. Okay? What that means is that each of these vectors is an eigenvector, right? With the eigenvalues equal to lambda 1, lambda 2, lambda n. So in order for a matrix to be similar to a diagonal matrix, the diagonal entries, those lambdas, must be eigenvalues of matrix A. And the columns of matrix P must be eigenvectors of matrix A. And so what this reasoning leads us to is the following theorem. An n by n matrix A is diagonalizable. I haven't defined that word, but diagonalizable just means A is similar to a diagonal matrix D. Okay, so if we use the word diagonalizable, that just means that the matrix is similar to a diagonal matrix. So A is diagonalizable, A is similar to a diagonal matrix if and only if there is an invertible matrix P given by P equals x1, x2, xn, the columns of P are x1, x2, xn, where those columns are eigenvectors of matrix A. Okay. Moreover, if A is diagonalizable, if this matrix exists, then the eigenvalues of A are the diagonal matrix of matrix, or the diagonal entries of matrix D. Okay. So what we've just argued, what we've just shown, is that if we want matrix A to be diagonalizable, if we want to be similar to a diagonal matrix D, then the entries of matrix D are going to be eigenvalues of matrix A, and matrix P, the columns of matrix P, where P is the matrix that gives us our similarity relationship, the columns of matrix P must be eigenvectors of matrix A. All right. Now notice this actually puts a limit on when a matrix can be diagonalizable. Because in order for matrix A to be diagonalizable, matrix P here, which has the eigenvectors of matrix A, it has to be invertible, which means all those eigenvectors need to be linearly independent. We will see that there are times when we can find n linearly independent eigenvectors of matrix A, in which case matrix A is diagonalizable. It would be similar to a diagonal matrix D. But there will also be times where matrix A does not have n linearly independent eigenvectors, in which case matrix A would not be diagonalizable. There would not exist an invertible a diagonal matrix D that matrix A is similar to.